Hey there, this is Brom Bresenham. I'm working on a game called Axor the Mighty. I just finished my first week of development in the Godot engine, and I'm starting this weekly devlog to log my dev. This was the first week of Godot-based development, but Axor has actually been in development for 4 years. In the past, it was a part-time project, but beginning with this switch to Godot, it's now my full-time focus. Axor is a fantasy-themed, tile-based, tactical gladiator combat game. It is turn-based, and yet it still offers a fast-paced and streamlined experience. Axor was primarily inspired by the mobile game Inyo, although Axor is faster-paced and, among other things, adds direct combat to the indirect combat of its predecessor. Up until now, Axor was developed using my own computer language called Rogue, and using my own game programming framework called Plasma Core. Rogue is a general-purpose, object-oriented, garbage-collected language. It offers high-level syntax, but it compiles to straight C, and plays well with C++ and Objective-C. A game framework is similar to a game engine, but whereas a game engine is a one-stop shop that can manage everything for you, a game framework is more limited. A game framework is a collection of APIs that let you easily load assets, draw graphics, play sound and music, and receive user input. You still have to manage your own game data and create your own rendering algorithms on a per-app basis. To sum things up, the original version of Axor was programmed in Rogue and used Plasma Core as an abstraction layer between Rogue and OpenGL. I'll refer to that original version of Axor as Axor GL. Axor GL was in a solid alpha state. The game design had been hammered out, and the game was fully playable and close to feature complete. There was one big piece remaining. While all of the art had been completed, made by the excellent Owl Studio, the user interface art had just dropped and was not yet integrated. I developed and maintained various iterations of Plasma Core for over 15 years. I enjoyed the work. I loved allowing my games precise control over the rendering process and being able to add features to directly support my game dev needs. But keeping up with the advance of technology on the wide variety of platforms has turned into a real grind. While I was slogging away at updating Plasma Core's rendering system from OpenGL to Vulkan, I took a break and tried out the recently released Godot 4 engine. I took an instant liking to it. Godot has a great look and feel, a novel and powerful node-based architecture, a stable, elegant, extensible, and mature open-source code base, and it supports all major platforms. I decided to remake Axor in Godot for 3 reasons. First, to gain instant access to Vulkan-based rendering and broad platform support. 2, to refactor my game architecture like I'd been itching to. 3, to leverage Godot's excellent controls library to implement Axor's user interface. However, I'm not remaking Axor purely in Godot's GD script. Using Godot's GD extension native library system, I'm keeping Axor's game logic and game state in Rogue. I'm even rewriting Plasma Core to be an abstraction layer between Rogue and Godot, rather than Rogue and OpenGL. I am shifting all of the presentation logic to Godot. For example, in Axor GL, it was Rogue code that decided how to draw the current frame of lava. In Godot Axor, a node-based scene composes the lava tile, and GD script controls its animation over time. I got a lot done over the first week. I had started working on Plasma Core GD, so to speak, a week earlier, week 0, we'll call it, with a number of Rogue language improvements to support it. In week 1, I continued to work on Plasma Core GD, continued improving Rogue, wrote some basic Axor game infrastructure in Rogue, and developed 4 complex game tile nodes in Godot. Here's what my game looks like after all that. It doesn't do anything yet, and the layout algorithm is very simplistic, but I'm quite happy with where it's at. Let's take a look at a number of things. First, I'd like to point out that the default panel arrangement in the Godot editor really slows things down, as you have to constantly move your mouse between the left and right sides of the screen. The only sensible arrangement is to put both panels on the same side. Tap the ... ellipsis button in the corner of each panel to move it. Be sure and save your layout under Editor Layout to easily apply the new arrangement to other projects. Notice how my lava ground tile is animating and spawning flames as it's just sitting there in the editor. That's because I've added the @tool fairly to the GD script, which causes ready and process to be called in the editor, not just at runtime. There are some caveats and limitations to this technique, but in many cases, it's a great way to see instant feedback on your code changes. After a tool script is loaded, ready won't be automatically called when you make changes to the script, so I suggest mapping a key combination such as Ctrl-R to reload the current scene. You may also need to make use of the engine.isEditor hint function to find out if the script is running in the editor or at runtime. When a script is in tool mode, exported property setters are called as soon as you change the value in the editor. Besides being useful in general, I like to make simple buttons out of exported Boolean checkboxes like this. In tile-based terrain, it's easy to spot the repeating patterns when you use a single tileable image for a given type of terrain. You can make the tiling less obvious by using 3 or 4 variations, all of which connect seamlessly on the edges, selected at random. I did that with my sand tile here, but instead of having 4 full-size tile variations, I have 4 quarter-size variations. Each sand tile is made of 2x2 quarter tiles, with the variations selected at random. To accomplish this in Godot, each quarter tile is a copy of an animated sprite 2D node, with all 4 variations as frames. Each quarter tile is set to a random frame when the sand node is created. The lava ground tile and the wall tile share something in common. They both use tile variations to connect adjacent lava tiles and wall tiles, respectively. You might expect that they use a 4x4 connecting terrain system with 16 tile variations that handle 16 possible layout combinations. In fact, they use a smaller and more flexible system based on 13 tile variations that handle 256 possible layout combinations. I'll explain both things. Here's the good old arcade game Gauntlet 2. It has very nice walls and it uses a 16 tile system. The idea is that each wall is adjacent to a wall or non-wall in 4 different directions. That's 2 possibilities, wall, non-wall, in 4 directions, giving us 2 to the 4th, or 16 possible combinations of how a wall needs to connect to its neighbors. You draw 16 tile variations, and you can handle anything in 4 directions. A 4x4 wall set like this doesn't handle connecting to diagonal neighbors. Each variation basically assumes that the top left, top right, and so on are not walls. So if your game needs to allow 2x2 clusters of walls or larger, the blocks of walls essentially have holes in the corners of each tile. We can't easily scale up our number of tile variations. If we allow diagonal neighbors, that's 2 possibilities in 8 directions. 2 to the 8th equals 256 tile variations we'd need. Here's the trick. Use quarter tile variations, because each quadrant of a tile has fewer variations to worry about. Here's the 16 tile variation pattern. And here's the 16 tile variation pattern split into quarter tiles with duplicates highlighted in yellow. There are 64 quarter tiles there, but only 12 of them are unique. If we add a 13th solid fill tile, we can handle all 256 variations of connecting tile using those 13 quarter tiles. Each quadrant of a tile is handled separately. For example, for the top left quadrant of a terrain tile, we'll need to check for neighbor tiles up, left, and up left. The lava ground tile uses this system, with 4 alternates of most of the 13 tile variations for variety. That's why the sand tile needs to use quarter tile variations, so that the sand on the sand tile matches up with the sand on the quarter tile lava edges. The wall tile uses a variation of this system. There's a single front-facing wall tile, and then the 13 tile system is used to draw the wall tops. Because a single tile to the left or right doesn't have a wall top tile above it, the connection logic ends up being slightly different. Lastly, I want to show off a couple of interesting things regarding the lava wave tile. First, let me demonstrate how to make the shader for this tile to get the wave motion. Let's make a Mesh Instance 2D quad with a lava texture, scale it to the pixel size of the texture, 200 by 200 in my case. Create a new shader material in the canvas item material property. Expand the shader material and create a new shader. I like to use visual shaders as I don't need to know the Godot shader syntax to work with them. Click on the shader to open up the Shader Editor panel. We want to manipulate vertex positions, not colors, so let's switch from the default fragment shader to the vertex shader. Right-click to add a node, search for vertex, and choose the vertex input. Let's pipe it straight through to the vertex output to make sure we've got the right thing. There's no change to the mesh, so that means we're good so far. On the vertex input, click the arrow to the left of the eye to drop down the separate X and Y inputs. Currently they are mislabeled as red and green, but they still function as X and Y. Instead of piping through the vector2 as a unit, let's send the separate X and Y inputs to a vector compose node and send that to the vertex output. So far, so good. Now let's vary the Y position over time. Taking the sine of the current system time will give us a nice oscillation. Add a time input, send that through a sine node to be the A input of a multiply add node. Hook the Y input, green, to the C input of multiply add, and have the output of multiply add be the Y input of vector compose. Now we see a dramatic oscillation of the entire image. The mesh instance 2D has size 1, and we're adding the size functions +1 to -1 over time. Let's reduce the oscillation movement. Change the B input of multiply add from literal 1 to literal 0.02 so that sine is oscillating plus and minus 2% instead of plus and minus 100%. Now let's make the image oscillate a little faster. Multiply the time input by 4 or so. To get the wave motion, some vertices should be moving up while others are moving down. We can accomplish this by shifting the sine function time input by the x position of the vertex, or the horizontal position. Create another multiply add node. Send another copy of the x input, red, to be A. Send the result of the time multiplication to be C, and send the result into the sine function. It's getting there. The mesh instance 2D currently only has 4 corners, so let's subdivide it horizontally to get more points of articulation. 5 subdivisions looks good. Lastly, we need to figure out a scaling factor to get the edges of consecutive wave tiles to line up. Duplicate the mesh instance 2D a couple of times and arrange them side by side. Let's adjust the B scaling constant of the last multiply add node we made. When I first implemented this, I started essentially just doing a binary search. 4 was good, 5 was better, 6 looked better, 7 was too much. Then my limited mathematical intuition told me that the answer must be a multiple of pi, 2 pi to be exact. So, use a software calculator to copy in the value of 2 pi, or 6.283 is close enough. Or there's a pi shader node if you want to go that route. Finally, let's look at one more interesting trick I'm doing with my lava wave tile. Here it is without the shader wave. Notice how the texture is subtly animating over time. It's a 2-layer effect. Here it is without the top layer. I have 10 lava animation frames that are fairly choppy on their own. What I do is I draw frame in on the bottom, and then I draw the next frame, n+1, on top, with some level of transparency. The transparency is scaled from 0.0 to 1.0 as the time interval between frames progresses from 0.0 to 1.0. Alright, that's a wrap on week 1. I'll be back here next week. See you then.